Martin here. It's a pleasure to be here. So this work is conducted in collaboration mainly with Alexei Vladimirov and Valery Bertone, which is now in Pavia. So we had a kind of preliminary work last year, and now we are continuing actually on this path. The outline of my talk is the following. There has been a lot of progress in our knowledge of TMDs from the 70s up to now. And some things are now established, at least for some kind of TMDs. We have the factorization for TMDs. But what is really difficult, or the point of the discussion now, is the implementation of the TMD formalism for a fit of TMDs. So this is the outline of my talk, and this is the code that we have started preparing. It's called Artemide. And okay, we have a version last year. We have updated it now, including, as we said, the way to implement the evolution in particular. And now we are working with this version to return the fit and see what are the information that we can get. The code is public, can be downloaded in our Spanish webpage, and of course, if you do not if you do not manage to do it, just give me a call. So.
No, it works, it works.
It works. That's the difficult, really. Everybody can find it. So there was a kind of a joke of Ted this morning that probably nobody realized, is that when he wrote the cross-section, for example, for Drellian, which is a concept like this, and he said, okay, we know everything basically, these are 2 loops, these are 3 loops, blah, blah, blah. So now we can just go and fit it. Actually, it's 5 years that this formula is around, and nobody has implemented up to the order that we are. So things are not so easy, and actually they are pretty difficult at some point. In the sense that there are a number of subtle points that one has to take into account when making the fits. The cross-section, for example, this is a kind of Drellian process. In fact, is split in a series of pieces which should be included all together in order to have a proper fit. First of all, is this stuff here is a lepton tensor cuts. Every experiment in Drellian, you measure electrons or muons, and your phase space has some cut. This usually happens in every experiment. It's definitely important to consider this for LHC, and often in older experiments we do not have this kind of information. So if the new experiments are done in this sense, so this is an important information. Electroweak charts are very well known. Hard coefficients are known up to 3 loops. And then there are these TMDs. And these TMDs, they are divided on its own, on a piece, which comes from the evolution, and finally a non-perturbative low energy structure of the TMD. This is not the end of the story, because we know also the asymptotic limit of these TMDs. When the transverse momentum is big, or correspondingly, the impact parameter is small, this TMD can be broken in a coefficient, which we call the matching resistor coefficient, the collinear PDF, and finally, there can be also, in this implementation, a non-perturbative input that we do not know. So there are a lot of pieces that we should put all together, and the way you put all together can be crucial. So one of the most important pieces that we have is the evolution factor. And the evolution factor goes together with this matching with some coefficient. I will not consider these white terms here, which are factorization terms. I will not consider them theoretically, and I will not consider it practically, in the sense that I will try to select data such that for augmenting these terms should not be important. This is a kind of first thing that we have to take into account.
Yes, but why did you call it factorization breaking term?
Because we don't know if they are factorization consent. So in the sense that these terms are a higher order in the power expansion, and we do not know if factorization is preserved by this kind of expansion. So in principle, these terms are factorization breaking. There is no demonstration.
Right.
Pardon?
In terms of transverse momentum.
In terms of transverse momentum, yes. So these terms here are much are probably incompatible with the TMD factorization. So, but I do not have a proof at the moment. So, yes. Of course, the question that has raised in the previous talk is about the non-perturbative structure of TMD beyond the PDF. So PDF encloses part of the non-perturbative information, but the TMD factorization theorem tells us that there is some non-perturbative information which goes beyond PDF. Now, here you see I put a Z and a B. So these information is this is the general structure of this information. Can depend on Bjorken variables and can depend on transverse momentum. Of course, there are several hypotheses which I will discuss. Let me introduce a bit the evolution. This was stated in the main talks already. We know that the evolution of the TMD is actually a bidimensional evolution. An evolution in the renormalization scale and an evolution in the rapidity scale. The two evolutions are connected in the sense that if I take the anomalous dimension here and I make a successive derivative into the rapidity, I recover the gamma cusp with the minus sign. And the same happens if first I take the rapidity anomalous dimension and derive it with respect to the renormalization scale. I also get the gamma cusp. Yeah?
So the big F includes a soft factor.
The big F includes a soft factor.
So why isn't the soft factor free of rapidity?
The soft factor is included here.
No, that combine soft factor with a collinear term shouldn't be free of rapidity.
It is free of rapidity divergences. But the point is that this rapidity scale is a kind of a separation. It works like a factorization scale between ultraviolet and infrared effects. So that it has a different origin with respect to the usual factorization scale. And so it follows its own summation. Okay. So this is so far so good. This is something that it has also textbook, Collins book, and so on. And this condition that we have the double derivative mentioned to the cusp anomalous dimension is important because it ensures that, say, in order to establish the evolution, I want to start from a rapidity scale and a factorization scale and finish in the rapidity scale and a factorization scale. And the double, this equation here allow me to go from the initial point to the final point independently of the path. Just choose the final scale. So if this is true, then I write the evolution factor, which is of the same kind that we have seen in several talks today. Probably this D corresponds to K factor divided by 2 of call it. So if this is true, then because I can go from the initial point to the final point in a path-independent way, I could choose from phenomenology the path that I like. This path, this path, this path. Now, if one checks in literature what people chooses, and there is a slight preference for one of these paths. It's this. Why don't they choose the other one? It's the same. The point is that this equation here is not exact because we know this anomalous dimension up to a certain order in perturbation theory. So that up to that order it works, but then it works anymore, and because of this truncation, the path independence is lost. And the fact that the path independence is lost is can be, I mean, one can make a simple plot using the evolution factor without resummation or with resummation. You see that the three paths that I've shown you before have actually a completely different behavior in this space. Of course, the effect is reduced when we have a log resummation, but still can be important, especially when we analyze the LHC results, which are extremely precise. So the restoration of path independence is something that we want to achieve. There is a nice formalism to show this. And I like to show it because it's very nice. So sorry for. It's very nice because it takes into account that these two scales can be put on a vector, which we call nu, so that now the evolution equation appear like a differentiation operator. I can differentiate with respect to the factorization scale or the rapidity scale. And I can also build a curve with respect to these two derivatives. Now, the evolution matrices, the anomalous dimension and the d rapidity evolution, can be put together also in a vector, which we call now the evolution field. And the evolution equation appears just the gradient of the TMD equal to the evolution field times the same TMDs. And the integrability condition on the otherwise is that the curl of the evolution field is equal to 0. On the other side, when we recall all our classes of dynamics, this means that this evolution field can be expressed as a gradient of a potential. And at the end of the day, the evolution factor is just the difference in the potential between a final point and the initial point in two-dimensional space. And this is the evolution curve that we know. Now, if we study this potential, we observe that there are some singular points, like there is a Landau pole, which is here. On the left-hand side is actually not shown. But then there are what are called equipotential or null evolution curves. In other words, because the evolution factor is just the difference between the potential, we have curves on which the potential keeps constant, are just curves, and there is no evolution. And these, which are drawn here as all the evolution curves, and there is a saddle point, which is a special null evolution curve, which satisfies this kind of equation. So this is a very nice picture. And the point is, what happens when we truncate, when we break this picture? What happens is that when we make the derivative of this d function with respect to mu, we do not get anymore the Caspar anomalous dimension. We get something else which include higher order terms. The type of correction depends if we have a resummed factor or the unresummed one. But what is really scaring is that if I consider the log of the ratio of two evolution factors between two different points and with two different paths, say here the points, initially and final points are the same, but the paths are different. Now I can express this in terms of this difference here, and it comes out that this result is proportional to the logarithm of the two rapidity scale. So the more the two rapidity scales are different, the more this factorization breaking terms are important, which is a bit a disaster. So restoring the integrability condition is crucial. Now, how can we restore? Let's go back to our electrodynamics course, and we have that fields that can be decomposed in a conserved field by plus something else. If something else has different properties, and in practice, the good potential is the one which is conservative, which can be written as the gradient of the potential, while the other part describes the factorization breaking terms. Now, we would like to express the evolution factor just in terms of a potential which is conservative. This is a statement that integrability condition is restored. Now, how can we do it? This, although not expressed in the same terms, but this story is already taken into account basically in some implementation of the evolution factor. So the usual implementation is what we call here improved D. Basically, we have this evolution factor which goes from initial scale to final scale, and then we add some non-perturbative fact. This is a standard way. Another way to do it is instead to modify the anomalous dimension such that we quit the terms which break the factorization. So we go from the standard anomalous dimension to a modified one where we make some subtraction. Of course, no one of the two methods I think is inconsistent, and but we have studied this in order to see if we have some advantages with this method. So this is what happens in the classic scenarios of the usual implementation of TMD. You have to choose a scale where this integral is broken, is split in two, and then if from this we recover building the potential, what we are doing is actually the following. Actually, we start from a path up to a certain mu0, then at some point we switch the path and we go to the other one. Of course, everything is, what is crucial is the choice of mu0. mu0 can be put at the initial point or at the final point. This is the origin of the two kind of paths. Okay, so if we want to have fits using this kind of evolution implementation, we have to agree universally on the value of mu0. We agree on some universal value so that this path is fixed, and we can work with that. There is another possibility. The other possibility, now we modify this anomalous dimension. So we have the potential is just the indefinite integral of this. And the evolution now depends on the initial point and the final point, but there is no other intermediate point. There is no mu0, just by construction. So in some sense, this is nice, because this parameter is a kind of fake, it's a kind of convention-dependent parameter. And we can avoid the introduction of this parameter in this way. The path dependency is achieved anyhow. And what is a bit more subtle is that we have a more clear separation of the non-perturbative part of TMD and its evolution. In the sense that when we introduce this mu0, we have to introduce also some say the fit depends crucially on this mu0. So there is a non-perturbative input that we insert by hand, and this is avoided with this kind of procedure. So it seems there are some advantages. So let's see how we can proceed. The idea is that from the initial point now, we can evolve on an equipotential line with final point, an intermediate point. Evolve is actually nothing badly said, because we do not evolve at all, because the line is equipotential, so that the evolution factor is actually 1 from this point to this final point. Then here, we can just make the evolution on a shorter wall. In this sense, we should achieve a more stable evolution factor with respect to the perturbative oscillations. Okay.
This one, this evolution path is one. Is this statement that is purely perturbative or
I also included
even non-perturbative the evolution path is still one.
Yeah. Yes. Okay. Now, so conclusion of this part, more conclusion. The TMD depend on a couple of points, okay? So a couple of points in this evolution space, and so two TMDs which belong to the same line in this space are actually equal. So the evolution just connects pieces on different line on this evolution space. The question is there a line which is better than the other? Now, okay, we have some reasoning, because this TMD should be broken in a coefficient and a TMD, and this operator expansion introduces a new scale, and now this new scale is related to the renormalization scale that we had before. And okay, we can argue, I want to enter here, that if we choose as the initial point, the setter point, actually we have no restriction on this scale of operator expansion. So we have a freedom to vary to whatever we like. So we would like to stay here. The final prescription that we want also to achieve is this zeta prescription. In other words, we want that, if possible, this TMD has a null evolution with respect to the normalization. This can be done choosing a particular value of the rapidity scale. So this can also be done. So all this to say that when we fit TMD, we have to look at errors. And there are many sorts of errors which can come and can depend on the way we implement the TMD. So the classical implementation of TMD, we have figured out 4 types of error: hard scale error, a low scale error, a rapidity evolution error, and the matching at a small. All these parameters should be varied in order to check that we have correctly implemented our perturbative information in the implementation. Now, with the other alternative proposal that we do, actually, we avoid some of these parameters. Just because this C1 is the measure of this mu0, which we do not have anymore. And actually, this C3 was one of these scale, and now it's included already in the other scale. So using this optimal definition of the TMD, we can merge this scale into the number. What's the result of this? We have done it, for example, for LHC data. This here is the variation of all this scale, and this is the amber. And this is the scenario where the other implementation. So that this C1 is absent, this C3 is also absent, and we have just this C2 and C4. And we have the amber. Now, what's the difference between this figure and the other figure? The main difference is not the amount of error. The amount of error, let's say we do not reduce the error of an order of magnitude. This will be also linear from a physical point of view. Okay, what we reach is a more stability of the error. So, for example, this error here, which is responsible for this waving, is now basically absent, while here the error is basically constant. Okay, so we avoid this kind of strange oscillation of the error that we had before. This is for CDF. Here the story, here this kind of oscillation were even more crazy. And now you see, but these numbers are not 1 or 2 micron less. It's a bit less. And this is for low energy. Okay. And also in this case, we have more stable choice. First part of the talk is gone. Now, second part of the talk. Second part of the talk, which I will treat about something which have been also treated in other talks, is about the non-perturbative models of these TMDs. So we have our TMDs, coefficient factor, PDFs, and this stuff. Now, our findings is that the form of this non-perturbative correction to the TMD really depends on the kind of data you like. For example, E288 eta are sensitive to a broad range in BT space. Okay, while for example, if we just limit it to Atlas data, the range of BT space to which these data are sensitive is much shorter. So the Gaussian behavior that is usually stated for TMDs actually works for us only for high energy data. But for low energy data, they really prefer an exponential form. So we look for models which modulate between a Gaussian and an exponential. These models can be also X-dependent, and we are now currently testing this. Okay, so it can be that the width of the Gaussian and also of this exponential case depends on X. And this we have found that happens also for the non-perturbative part of the evolution. Actually, if you take this DMP like this, like a BB star, then we see that for small b, this goes like B square, and then it goes linearly in B. So it also reproduces this kind of behavior. This figure also tells us, well, I already said, the 2 experiments are sensitive to different regions of B space.
Slides, the same. So the FMP factor is inside the convolution.
Yes.
I mean, will it be difficult and so will it be different to keep it out of the convolution?
Yes, of course, it's much different. You can keep it out of the convolution only if it is independent of it.
But I think, for example, in the PPR, we have FMP multiplies the convolution, but it's FMP of X. It's not convoluted.
Okay, I mean, I'm not strict about this. Depends on how you want to recover the asymptotic limit of this stuff. So this stuff is put here with the limit that when b goes to 0, this goes to 1. So that when b goes to 0, I have just PDF and coefficient. Okay, as far as you're consistent with this kind of limit, I think you can. We have to do.
It should be so, right?
It should be so.
I mean, factorization theorem, I guess, states basically this.
Yes.
And it's physically understandable because this is the collinear limit. So
yes.
Why should we care about it?
Yeah.
No, but okay, so the condition that Vt equals 0 is equal to 1 is one thing. What Andrea is referring is the argument of f and p is z in that formula, which
yes.
is inside the integral of the convolution.
Yes.
It is not x, the argument of the left hand side.
So
We normally take, in our field we took f and p x.
I think there is no. I think the only theory constant that I can imagine is that when b goes to 0, this stuff is just PDF and coefficient. As far as you respect this, and then, of course, one fit is better than the other.
but you don't say
which one?
You know which
Vabbè, I continue. Now, another crucial point that we made here is that the factorization of the cross-section actually happens only when the transverse momentum is much smaller than the electron mass. What does it mean? We found that for the data that we took, this ratio of transverse momentum or electron mass should be less than 0.2. Now, we are going to analyze Atlas data, and I will not show any result with Atlas data at the moment because it's still a work in progress. And the point is that Atlas data have a precision of a per million. So is this criterion sufficient, or do we have to do something else? Because when we are at the precision of per million, there are other stuff which come in. No, it's not here. Like QD corrections, again, we speak about this. There are factorization breaking terms, which can be of the same order, 3 corrections. So Atlas data can be problematic because of this extreme precision that they have. Another point that we are trying to make is a more correct, more formal statistical treatment of the data. So experimental results usually come with a central measure that we have statistical error, uncorrelated systematic error, and correlated systematic error. And all this information should be used on top of the perturbative information that we had before. Now, using these, we can make the correlation metrics, and now we are trying using the correlation metrics to calculate the chi-square. So this is a bit more consistent, more appropriate treatment of the data. Now, there is a point that also has been spoken about, is about the normalization of data. Cross-section usually are not normalized. So one can ask if this chi-square can be done as, so if we can predict actually just the shape, or we are going well also with the normalization. So the way to statistical treat this is analyzing the systematic shifts. So especially everything in terms of Bayesian parameters, uncorrelated uncertainties, and shifted theoretical prediction. And I will show just some plots. I don't want to go bother with formulas. And the plots are astonishing. So this is, for example, well, it starts with this. This is INT-18-3, and we see that the theory without shifts and the theory with shifts actually say, if we do not consider the shift, it seems that we are really off the data. But when the shifts are included, and we're speaking about a 30% shift, it's our line actually really go on the data. For Atlas, we take 2 experiments of 2 set of data of Atlas. These are just something to show. And really, depending on the experiment, the shift can be bigger or lower. But it has an important part, especially because the error here is extremely small. So taking into account the shift is the only way to make a fit of all LHC data, I think, including in a proper way. So I will go to conclusion. I think I'm in time, no? More or less. So we have, when extracting TMDs from experiment, we have first of all to check the limit of factorization, so that we really go where the TMD factorization theory actually applies. Some set of data are extremely precise, like the Atlas data. So for this data, one has to think ahead. If to include unfactorizable terms, Y terms, or other collection, QED, or things like this. Other data are less sensitive on this stuff. Scale variations are important. An optimal implementation of the TMD evolution is crucial to extract data. The difference is a good fit or a bad fit, or something which really works or something which really doesn't work. PDFs is also an important issue. In all of the extraction that I did before, we match with some PDF which are taken by someone else. Now, different sets, different replicas provide different results. So there is also an error which comes from the extraction of PDFs. Now we're speaking to series and to fragmentation. This will be fragmentation errors will be another important issue there. And finally, model building. Model building, I'm very unhappy about this because it's still something which goes with the procedure of guess and try. And we have a very, it's not systematic. So we do not have yet a systematic way to achieve the particular part of the TMDs, and we should work on this. Lattice is working on this, but still a long way. So these are my conclusion. We are trying to analyze at least Dralian at an express reading order, and to extract so the unpolarized TMDs in full glory. Atlas and CMS had, I don't think Atlas have data 13 dB complete, and CMS neither. Probably this slide is old. Say they were not used up to now, at least. It is important to combine high energy and low energy data, just because each energy sector is sensitive to a different part of the TMD in impact parameter space. The choice, the way to implement evolution is crucial. I've shown two kinds of choices. Each one has its own good feature, hopefully. So this is something that we have should be under control, and is fundamental to fix the error of our analysis. We try to include all these in Artemide now with in 1.3, but we are working for a new release which improves the statistical analysis, especially for LHC data. At some point, probably we'll try to do also Compass for Dralian and series, and of course there is a long way for study processes with jets, and you know, that's it. Thanks a lot.
So Ignacio, I have a question. How is it that you can select data